rest of the class joined in, right? Cool. We're at the last project, which is the last kind of thing that Professor Cooper is telling you, you have to do it this way. And then module 5 is you telling me this is how I want to do it. My goal, like when we get back after Thanksgiving, so not next week, in 2 weeks, is more advising about like, hey, how do I do this? How do I set this up? Does this make sense? Answering those kind of questions. So this is the last time where I'm telling you, like, do it this way. Here's how to make these plots. And next time you can say, like, I want to do it my way. I want to do something interesting and cool that I think is interesting and cool. Not that weird Professor Cooper guy. So yo-yo de-spinning. This is an awesome, like, mechanical engineering, just pure conservation of angular momentum thing that works so well. Like, it's such a cheap and easy to implement, like, rocket science kind of problem. Yeah, let's take a look at it first. Then we'll talk more about logistics after. So on this, like, I know I'm using YouTube to show you YouTube, and then maybe I'll show a YouTube clip of us watching YouTube reaction videos, maybe. But as this spaceship takes off, like, the thrusters, just due to the fact that you can't build something to just not rotate. Like, we're not directly applying a torque on this thing, but there's always gonna be some torque applied, whether that's due to wind or just the thrusters slightly misaligned, and now you're trying to go up, but instead you're going up and spinning. So no matter what you do, you're always going to start spinning. And sorry if this is causing any motion sickness for anybody. So it's spinning, 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 and then it's almost instantly when it releases these little yo-yos. So Mach 3, yeah. And now it's kind of spinning backwards, right? So as the yo-yos like shoot off, all that like spiraling motion is done, just completely gone, which is pretty amazing. And this isn't like with you're not using any fuel. Fuel is expensive. These little yo-yos are very cheap, and you don't care if you like send them off. So it's a great like conservation, angular momentum kind of yo-yo de-spinning problem. So how do we do this? So now we're going back into NanoHub. So we have like interactive Jupyter notebooks. You can also get there anytime from this like rocket button. This one's kind of appropriate because it's like rocket design using that rocket launch. And then it'll bring you back to that NanoHub engineering dynamics. And we want to come down to module 4, project 4. And if you want more background information, there's also this like yo-yo de-spin design intro that shows you where these equations are coming from. But to get started, all we need is that first project 4. So I'm going to go through and run everything and kind of describe what's going on, like what's happening here. And again, I'm going to change, like after this election, I got to change this stuff. I just can't support like Tesla anymore. Like not that this project was like supporting Tesla, but it is kind of a weird and interesting engineering problem. Like there's a car in space now because an eccentric billionaire sent it out there. And so the thought is like, okay, well, the spaceman that's in this car probably has bad radio reception because it keeps rotating. So let's de-spin that Tesla. That's the goal here. And again, I'll find something better to de-spin for next time. This one's too politically charged now. With like and main things that are going to affect like the despinning process is really like the moment of inertia. Like how much torque does it take to get the thing to spin or get it to stop spinning? So we're going to use these yo-yos as basically a counter torque. So give all the angular momentum to the yo-yos so that our roadster stops spinning, and now we can get XM radio, and now he can listen to Joe Rogan again. And then the other things that might have an effect would be like this little m is the mass of the yo-yo. So right now it's just like 10 grams. And that W0 is how fast it's spinning. So it's doing 15 radians per second, like a little more than 2 or almost 3 cycles per second. So like 3 rotations per second, something like that. And we'll combine some equations, do some fancy math, solve for what the final time to release the yo-yos is. That's what that TF is. And now what I'm doing is from the perspective of the person that is spinning. So like this person driving the car and they're spinning, they're like, this radio reception stinks. They're watching these yo-yos unravel around the car. So that's what the perspective, so it's like a fixed perspective in this graph, like the unraveling process. And it's only going from time 0 when the yo-yos get released to the time when I stop spinning. So that's when things kind of flatten out like that. So at that point, the car has stopped spinning and the length of cord gets detached. And now Joe Rogan is nice and easy to hear again, and as frustrating as ever. And now we can say, yeah. It's not anything against like the show, but it's become like the political like megaphone for like just things that I can't support. Like, I don't know, the anti like friendly sometimes. Like it's not even like specifically attacking one group. It's just sort of like, it's like there's a problem with everybody who's not a white male. It's like, well, is it? Or is it just that their white males have a lot of issues that they're like taking out on other people? Anyway. Again, I don't know how to get like Jupyter projects to like solve political problems, but here I am. So now I can look at like, this is the speed of like the car, like how fast was the car spinning as a function of time. And again, like that release point TF, that's the one that I solved for. That's like the ideal length. Like if the cord is that long, then at that point it'll release. Now I'm not spinning at all. If I design the cord too long, like, because sometimes as engineers the idea is like, well, if the cord was supposed to be 17 meters, let's just give it a little bit extra. Factor of safety, we'll give it 25 meters. But in that case, I would actually end up re-spinning the car, where the car is now spinning, but in the opposite direction, which is not ideal. So we want like an optimal length of cord, and then that is the solution. So let's go back and start changing things. Instead of a Tesla, let's despin mass of cow, 1,100 pounds. So like 600 kilogram, 550. So let's say the mass is like 550 kilograms. I'll start deleting. That's our 550 cal. Length, dimensions of a cylindrical cow. So it would be 1.5 meters high and 5 feet. I think that dimension's opposite, right? Yeah, that's what I want. This kind of cow. How big is a cow? How tall is a cow? So it's, let's say 500 centimeters. So half, or wait, 250 centimeters. So 2.5 meters long. And then, how wide is a cow? We'll call it 1 meter tall, about 1 meter tall. Oh, 1 meter tall. And then I want to say it's 25 centimeters, so 0.25 meters wide. And instead of calling it like a block, saying that it's width squared and height squared, really it's more of like an ellipse with one. So this one is going to be 0, or that one is 1, and this one is 0.25. So I want to look up moment of inertia of an ellipse. So it's m times a squared plus b squared over 4. Capital M times h over 2. Well, I guess we'll say h squared over 4 plus w squared over 4 all over 2, all over 4. Taking major, minor radii, kind of turning this cow into like a squishy ellipse. And ellipses and spheres, we use those. Physicists love to use those because it optimizes surface to area, which is a biological thing. Like you want the highest surface area for the lowest amount of volume. And I've got that 550. And then let's say the cow is like spinning wildly out of control. Instead of 15, we're going to say it's like doing 100 radians per second, just to change things up. So I'll run through. Over that same amount of time, like a lot more is happening. I think the path is like spinning for a while. I want to double check. And it looks like I didn't take enough time to release it yet. I thought that would be, I didn't think that would be a problem. Let's see. So it releases at, we're supposed to release it at 1.7 seconds and 6.25 meters. So let's increase our time. So instead of 0 to 1, I'm going to say 0 to 2 seconds. Oh wait, W is not defined. Oh yeah, because it should be W, capital W. There we go. That's more what I was expecting. All right, so I want to go back to, let's do half a second. So if you're spinning faster, everything happens faster. That's why I was confused why the path took so long to despin, but there was something else going on. All my variables didn't update because I had that error or something missing. So everything happened a lot faster. When I see like when did this thing get released, it was 0.13 seconds, so 130 milliseconds of despinning, which is closer to like what that rocket was doing. It was like less than 1 frame before the yo-yos were gone. And 3.3 meters of chord. Now if I go back up, like, all right, well maybe the cow's not spinning that fast. Maybe it is doing 20 radians per second. Let's see how that changes. Now we get like everything's happening slower. So the path of the yo-yos, we have a lot more data points that we're looking at each point over time. The release point is past when it's supposed to be. That's okay, we still get it. And I still get that the length of chord is 3.27 meters. There's no difference. It changes how long it took to actually get the thing to work, but the actual length of chord is independent of how fast I'm moving. And that part's kind of cool, because then you don't need a different yo-yo for every, you don't have to calculate like, all right, am I moving 11 radians per second or 11.5? Like I need a different yo-yo for each of those. Once you find one, that's it. It's just, that is your despinning mechanism. As long as you know moment of inertia of your spacecraft and how heavy the yo-yos are. Cool. So there's some questions here. So the main things that you can edit are create your own payload. So make a moment of inertia that you want to despin and describe like what are the dimensions, what's that moment of inertia, what axis is it spinning along. Like a cow doing front flips is very different than a cow doing corkscrews. Different moment of inertia. And then there's some questions to think about like as we're looking at these. Like this one. Let's get time increased again. Go back to 1 second. Why does the rotation rate become negative? So if I'm designing these yo-yos and I just let the chord increase, so it just keeps spinning and the chord just keeps getting further and further away, at some point my payload is now spinning backwards. Like it was corkscrewing positive, now it's corkscrewing negative. Why is that happening? What is like a mechanism that you could use to describe that? That's one of the hard questions here. And then some other things like as you're changing mass of the yo-yos, what are things that are changing? What are the values that are changing? How's your design change? And then whatever else, anything else that you notice or want to say like, hey, did you consider this? That maybe a cow is not a sphere or an ellipsoid? Yeah, why is that happening? And if you keep increasing that time, like go out to like 3 seconds or something. At some point, the yo-yos will keep pulling on your payload to the point where it's spinning just as fast, but in the opposite direction. Not ideal, but I guess you could use that as a solution. I guess it would depend on what your final goal is. Yeah.
Why does it do that?
Why?
It has that, but I don't see why.
Yeah.
Is that because they still have momentum, so if you don't let them go, they're going to just keep spinning?
Yeah, they still have momentum. Yep. Yeah, so momentum is a big part of it. Yeah, what else?
If you increase the moment of inertia so much that the momentum they have is opposite.
Yeah, okay. So there's something about like that, because momentum is being conserved, right? Like we have, so if we break this down into I payload times theta dot plus 2 mr squared times theta dot. So initially, everything is moving same speed, everything's rotating together. Our total angular momentum is that. And then as these things keep despinning, so as this thing, as we're trying to despin, the yo-yos have some like theta dot that they're rotating around our system at some, and for the most part, there's nothing slowing them down, because the only thing acting, if I blow this up, I have a tension, just connecting the yo-yo to the spaceship, and that's it. I don't have anything to slow down that theta dot kind of term. So whatever that initial theta dot was, it'll stay the same. So r squared, but r squared keeps getting bigger and bigger and bigger. And overall, angular momentum is a vector. So if it was pointing up at a value of 10, and then I make r 100, now it's got to be the original payload has to move backwards to make up for all of that, all the yo-yos taking up. Sorry, go ahead.
Due to the lack of solid, right? If the connections for the yo-yos were solid, you wouldn't have this issue.
If it was solid,
like if it weren't like a rope, it were instead like a solid connection that probably you wouldn't have the same issue.
like if we had,
Because omega y would just stay the same as there's theta dot would be the same for both.
like if it was spinning around on a rod and they kept moving further away. Yeah, because then everything would have the same amount of theta dot would be fixed, but they all have to rotate at the same amount. So that's one way to think about it, of like angular momentum is conserved. Like if I start with 10, I got to end with 10, even if my yo-yos have 100, which means my payload now has negative 90. So in total, HG, whatever it started with, has to be the same HG as before. Yeah.
So would it be like correct to think about this like transfer all the momentum to the yo-yo, the spinning momentum to the yo-yos, and then you let them go, so you're getting the momentum out of the system?
Yeah, that's like the ideal goal, is that all of your angular momentum is only in the yo-yos. So if you cut the cord at the design length, then your yo-yos have all the angular momentum and you have nothing left. Like your theta dot goes to 0, so you're not spinning anymore. Yeah, nice catch. Yeah.
So if you do like the rod extension, then it would still be spin, or would it?
It would still despin. That's like same experiment. Have you ever like had two weights and spun around on a chair, or on a merry-go-round? If you like let yourself weigh out, you're spinning kind of slow, and as you pull yourself in, move faster and faster. And figure skaters do the same thing. They start spinning with arms out and then pull their arms in to spin faster.
Would it like never really come to a big stop?
This one would slowly come to a stop. It would be like an exponential decay because it's like a 1/r² decrease. So in this case, it would be like we would have a theta dot, and then if this is 0, we would start off at some initial value, decrease a lot, and then our asymptote is the 0 that it stops spinning. So as engineers, like at some point, like, yeah, it stopped. It's not moving anymore. Because at some point, as you get 2 or 3 time constants out, it's basically 0. Friction will take over the rest. I guess in space we don't have friction, but we also don't have like, yeah, this would be more of an expensive structure, like have rigid beams connected. Yo-yos are nice because you can use like space grade fishing line and lead weights with 10 to 11 cents worth of material. You have a high-tech de-spinning mechanism. No control, no like PID controller, no computer implementation, just like a quick bam, de-spin, release the de-spinners. Yeah.
So the difference is the rigidity of the connector, not the fact that the yo-yo is actually spinning.
In those two cases of like whether it's rigid or not. So in this second case, it's assuming like if you had a rigid connection like that, then all 3 objects are rotating at the same rate because they're all connected to one beam that's rotating. In the case that we're considering, the payload and the yo-yos can rotate around at different rates because the strings that are attaching yo-yos to the payload, they have no bending stiffness, so they can curl and twist however they need to. And it's just centrifugal force that's like sending them outwards. Yeah. Other questions? We're just working through so far. Did anyone get an error yet? Something like interesting to solve? No? Or like my graph doesn't make any sense? It made me a graph, but not yet. That's like the fun stuff to deal with. Like, what's wrong? What did I do wrong? It's like, we're just doing science, man. Gotta get things wrong. But anyway, this is our main like Python setup. What's your mass? What's your shape? What's the moment of inertia? Yeah.
So 2 outcomes are always the release time and the program.
Those are our main 2 design outputs. So like this last, these graphs that are shown above, they're kind of giving us some insight into what's going to happen when we release these yo-yos. But in terms of like, what do I put onto my payload? So if I'm going to send my basketball into space and de-spin it, this is the thing that I need. I need chord length of 3 meters wrapped around, well here, in my case, it's a cow. But I need 2 yo-yos that are both 10 grams each and 3.3 meters of cord to de-spin my cow.
So does it mean that like once it unravels the full coordinate, it will release at that time, or even after it's already unraveled that cord length is going to be a certain amount of time before you use it.
This one, this design should unravel in 0.65 seconds. And when it reaches the end of that 3.27 meters, it's gone. It's detached
So
from.
those two are happening at the same exact time. So
Yeah, so 3.27 happens at 0.65 seconds.
you can change changing one to change another.
That's what you would think would happen. But if I take the speed and decrease it, go from 20 to 10, coming down. So that's my path of my yo-yos. So I'm going from 10 down to 0 in 1 point something seconds. So initially it was 0.65 seconds and now it's 1.3 seconds, but it's still 3.27 meters. So the time is going to change based on how fast I'm spinning, but the cord length is still going to be the same cord.
So what would you tell me the cord length is?
That one is based on like how much angular momentum I need the yo-yos to have. So at 3.3 meters, they have enough that it brings my cow to a stop. At least the spinning. It doesn't like stop the forward momentum. Yeah, in terms of like how do I know what that final length is? It's this I over 2m plus r squared, like where r is like the initial, like where I mounted the yo-yos to begin with. And in this case, really I should say like w over 2 or something, but w is okay. It's like, in my case, it's okay. But where you wanna mount the yo-yos. Okay. Just make like payload, try these things. Okay.
Yeah, go over it first, but have to compensate.
That one, so I use, at least in that first one, yeah, I use that one's for a car, like just assuming that a car is like a block. You can get better approximations of it. No. That one's for like an ellipse with a major radius and a minor radius. That is the inertia for the spin. I might have had it wrong, but radius, small radius squared plus big radius squared over 4. Oh, you got some means little w. Oh yeah, yeah. Yeah, what did you say? Yeah. Yep, okay. Yeah, yeah. Now bigger mass is gonna have now more it's interpretable for us. Yeah, it's a function of mass, right? Yeah. Yeah, it is nice.
The make them that so much easier.
Yeah.
That's right.
The payload itself. That one, like, is sort of a positive. Yeah, right.
I just the cow.
Oh man, the cow. Kilograms. Small planet. Maybe asteroid. Yeah, one person's trying to de-spin a surface warship out in space from the Navy. They're trying to figure out could you use the anchors to de-spin them and how much anchor would you need to de-spin a giant surface warship? There's a lot, yeah. Yeah, there's a lot of like the spiral kept going around and
Could you have like a different coordinate? It's over to half.
so if you change mass, we were just looking at that. More mass is going to be shorter cord. Less mass is going to be longer. Yeah. Okay. You can prove it wrong. That's fine. Yeah. Yes.
I just added another zero.
Oh, sorry. Yeah, there's two different masses. I was saying bigger, little m. So little m is bigger. Yeah, yeah. My bad. Yep.
Yeah, okay.
Yep. So when little m gets bigger, cord length decreases. Yeah. I guess I was assuming like once you pick the payload, it's not like you can tell them, no, just give me a smaller cow. This is our cow. She's the only one who's been for training. Yeah.
So I wanted to
Big with cheese. Nice. Yeah. Even bigger. Yeah. Okay. Yeah.
water's not there over there.
Yeah, yeah.
That's what you're listening to.
Yeah.
Yeah, it makes sense, so yeah.
Cool. And this is what it's supposed to play around with inputs and stuff. Yeah. So if you were like putting this, if you were putting this into practice, sometime, at least like for that video that you watched, they probably had like 50 or 60 of them. And then you release maybe each one at least 3 meters with little photograph maps. And you keep releasing sets of 1 or 2 periodically. Like you would almost be like blank, right? But it's a one-time use for it. Yeah. Otherwise, it goes into
Like I've always,
do we have room for 30 meters worth of cord? And can we still say that it's massless at that point? And if not, all right, then we'll make it, let's say we only have room for 5 meters to wrap around the hole. How big of a mass do we need? So usually that's how we go down. How's it going? Oh yeah. Oh man, the masses. That is amazing.
Yeah.
Sorry, that one's big.
Okay, so in here she's big.
Yeah.
Okay, and when I do that, it works, but then when I change it to a little less, right? Like it.
Yeah, because then you'd be saying, like at least that big eye,
Yeah.
the moment of inertia of, yeah, of your what you're trying to piece things.
Okay.
Yeah, and that's true. There's a little one there.
Yeah, that's why I was confused.
That's confusing. Yeah. Nice. Oh yeah.
Like dimensions.
Yeah. Cool. Is it full?
No,
Empty? Yeah. You want to use like a hollow shipping container, or
I just didn't think it was solid.
That's fine. Yeah.
It's hollow and I subtract things. So complicated, I think.
There is. I think you can look up like a hollow.
Yeah, and then do like
Yeah.
the outer minus the inner.
Yeah, you can do outer minus inner, but but I swear there's like a thin shelled. It's not in my list. This is usually my go-to list. Well, here's like a thin shell cylindrical is just m times r squared, but here we want shipping container. And that's the where did I get this one? AI seems to give us an answer that looks convincing, but there we go. But that one's still, it's not a thin shell. Yeah, all right. But that does bring up a good point of like we can use parallel axis theorem depending on how complicated you want to make your like shapes. Let's say I had like a person that I wanted to figure out what is the moment of inertia of this thing. Let's just say that it's going to be one big thing with a few point masses like that. So I can add up all the combination of each of the individual components, or I can subtract stuff. Like if there's like a missing, if I'm trying to figure out like a donut in the middle, then this one would be like minus that. You'd say like take the outer, take the big one minus the little one, and the moments of inertia you can always add and subtract moments of inertia as long as it's the same spot, as long as you're rotating around the same position. Here it's always like the center of mass of usually the biggest thing. That one is that little yeah. Yeah, that one. So that one is not showing you like the path because it happens like so fast. So you slow up a little bit with meters. Instead of 100, make that like 10,000. Yeah. So it's giving you the number of. Yeah, now you can see what happens in that. Because they don't, and the whole point is these funds in like 6 milliseconds because you're spinning so fast. Yeah. Yeah, but it doesn't change. Like this one still looks the same. Yeah. Everything happens. Yeah, when it hits that red point, that's like your design goal. Yeah.
10 milliseconds. It will have already traveled 6 meters away and cut the cord. Yeah. And if you change it, like if you make the initial spin smaller, then take that graph and move it further out that way.
Oh, so just do like one, no pink pictures, one.
Yep. Oh, I see. Yeah, I guess the only thing is like energy conservation. Makes it weird. Like if it was an energy thing, it would be like yo-yos get lots of energy and sooner or later we have zero. That's it. Here, yeah, angular momentum can reverse. Yeah. Yeah.
On the quiz, it says something about like forward momentum.